In this video, we will learn the intuition behind rotary embeddings and how they apply to machine learning and transformers, and we will also write some code that will implement our rotary embeddings from scratch. So let's say we have some words here. So I have words cat, dog, and fish, and in a transformer, each of these words will have assigned vectors. So I gave it some example vectors. So let's say we want to check the embedding of the word dog. So I'm going to say word embedding dog, and then I run this, and we're going to get, this is the embedding. Now let's say we have a sentence, dog is chasing the pig. This is going to be a very different sentence than if we had pig is chasing the dog. So it's important that in a sentence, besides each word having an embedding, we also have positions of each word embedded. One way to do this is just to make the AI learn a vector value for each position. And then for each position, this will always be the same vector value, no matter like how many times we are using the AI when we are using the AI. So for example, the first position in a sentence will have some determined vector value that will always be assigned to this position when we are using this AI. The problem with this is if we train the AI on, let's say, always 8,000 words, then if we want to generate 8,001 word, the last word will not have a positional embedding. So a good way to do this instead is using rotary embeddings. So let's say we have a coordinate system, and let's say a word dog is, let me show you, encoded like this vector. Now this is if it's on, let's say, the first place in the sentence. But if it's in the second place in the sentence, we will just rotate this vector by a certain angle. And if it's on the third place in the sentence, we will just rotate it again. So basically, we will take a vector of the word and rotate it by this angle, the number of times that corresponds to its position in the sentence. This is how we can encode positions such that we can generate even more words or even longer the context window than we trained on. So for example, if we trained on only 8,000 tokens in a context window, we can generate 8,001st token just by rotating it one more time. And we can generate unlimited amount like this. Now let's understand mathematics and intuition behind rotating a vector. So I drew this coordinate system, and then let's draw a vector that has dimensions 1 and 0, x1, y0. Now let's say we want to rotate this vector by a known value of theta. We know what theta is, the angle. So now we need to calculate x and y coordinates. So I'm going to draw them like this. This bottom one is x, and then this one on the side is y. So first, in order to calculate x, this is equal to cosine theta. So this is trigonometry. And then this y value is equal to sine theta. And it's also important to understand if we have a vector on the vertical axis, so how to rotate this vector. And knowing how to rotate these two vectors will help us rotate any vector. So let's understand how to rotate this one as well. So we want to rotate this by some angle theta. Now let me draw these lines to calculate this vector. So first let's calculate the x-axis. So as you see, this here x-axis is parallel to this component. So, and this side is sine theta because this side is opposite to the angle. So we can get this side, this is sine theta. Let me type this here. But one important thing is this is on the negative side of the x-axis, so we need to say minus sine theta because this is here. And then this side will be cosine theta because if we project it here to this axis, y-axis, we see that it's adjacent to the angle. This could be a bit confusing for those who are used to marking y-axis as sine and x-axis as cosine. But this is completely irrelevant right now, because right now we are calculating the sides of this triangle. So to calculate sides of this triangle, we take the adjacent side, and that's going to be cosine. So it's going to be cosine. The y-axis will be cosine. And the opposite side, which is corresponding to x-axis, is sine. And other markings are irrelevant here. So here is the trick I was talking about. Whenever you have any kind of vector, what you do is you decompose them into these two vectors, one vector on this axis and the other vector on this axis. And then if you just rotate these two vectors on these two axes, then you will automatically have this vector rotated by the same angle. So here I rotated this one, and here I rotated this one, and then this one gets rotated automatically. So that's what you do. So you're gonna use this transformation and this transformation together to rotate this vector. So this is how we do it. And this here is circular motion. This is not a straight line projection, so this is circular, is how I meant to draw it. So now let's take some vector 5, 2. So let's say this is like this vector here. And what we need to do to rotate it is we just need to multiply it with this cosine theta sine theta. And on this side, we're going to say this minus sine theta cosine theta. Like that. Now, the intuition behind this, I'm actually trying to grasp it, and I'm struggling. I think I'm gonna need a few more times or days to grasp this completely. But basically, since we are multiplying this vector with this matrix like this, that means, as ChatGPT explains, that this cosine determines how much of the original x-axis is converted and is kept in the new x-axis. And this minus sign determines how much of the original y-axis, this 2, is converted into the new x-axis, is added into the new x-axis. So this is going to make the new x-axis. And then this determines how much of the original y-axis, or sorry, x-axis, is added to the new y-axis, and how much of the original y-axis is kept into the new y-axis. So I'm also struggling to understand this completely, so don't worry if you don't get it. After a few times or a few more days trials, different methods, you will understand. Now you can read this if you want. This is a little bit of ChatGPT explanation, but I will continue our coding journey. So now let's explain this piece of code that will implement simple rotary embeddings. Now I import NumPy, and let's skip this function for now. Let's ignore this. Let's say we have an embedding vector, and this is going to be 1001. That's it. So let's apply rotary embeddings for different positions. So the position 0, we're going to call this function that I will explain. We're going to pass in the vector and the position. Same here and same here. So let's see how this function works. So we get the vector, we get the position of the vector. And then let's get the length of the input vector. So this is just the dimension. So in this case, it will be 4, because we have 4 characters. Then we will calculate the rotation angle based on the position. So as I said, let's start from 0.1, and then if position is 0, then theta will be 0. If position is 1, this will be 0.1, then 0.2, 0.3. So we will rotate the vector based on the position. Then create a new array of zeros with the same shape as x. So basically, we have np.zeros like x. That means that we will look at this vector x, which is this vector, and just basically replace everything with 0, and that's going to be our new vector. We will not replace into this vector, but we will create a new vector that same as this, but has zeros instead of numbers. look through the vector, taking 2 dimensions at a time. So we will go from 0 to dim, which is 4, because it's 4 element long, and then we will go 2 by 2. And we will just apply 2D rotation to each pair of dimensions. So this is what I explained in the mathematics part. So we take the cosine minus sine, and then sine plus cosine. And this is how we get the rotated x vector. Now, we're going to do this 2 times because the length is 4, and we go 2 by 2. So this will execute 2 times. So this is going to transform the first coordinate, the second coordinate, and then again the third coordinate, and then the fourth coordinate. So it will rotate this vector like that. If I change this vector so there are no zeros, because then it's easier to show. If I do this, we can see the rotated vectors that we get on these positions.